the next one is how to measure these earthquake waves. So seismometer. So by means of using seismometer, earthquake waves or seismic waves are measured. So here the graphical data acquired using a seismometer is said to be seismograph. Or seismogram, and the instrument used to record it is said to be seismometer. Conventionally, the instrument used was based on a torsional pendulum, in which a huge mass is suspended from one end, which is mounted on a frame, and that frame is connected to ground. Now it is a frame, and above the frame, so mass is suspended, huge mass. Is suspended, and another end of the mass is connected with a pin, which is in contact with the rotating drum, which is fixed on the frame. So this drum is capable of rotating. So suppose if in the absence of any shaking of earth or earthquake, keep in mind this suspended mass won't move because of its huge inertia, and so in the absence of any earthquake, pen will draw some white paper will be there on the rolling drum. So this is rolling drum. And there will be white sheet, white paper. So as the drum rotates, a linear line is drawn because pen is in contact with the paper. So this is in the absence of any earthquake. Suppose if earthquake takes place, this mass is not going to move even a millimeter distance, although it is connected to the frame because of its own inertia, it is not going to move. Whereas this part, rolling drum, starts to shake as earthquake starts, along with the frame in which it is mounted. Okay? So when a rolling drum starts to shake, you will not get a linear line. So now the line nature changes, some zigzag patterns are recorded. So this one, whatever first observed is P wave or compressional wave, and second signal is due to S or shear waves. So this is how a conventional. So it is actually connected with a time frame. So x-axis also represent time. So you will get signals as a function of time. That is amplitude as a function of time. It is a conventional setup. In modern devices, seismometers, it uses a sensor, linearly variable displacement transducer. Linearly variable displacement transducer. So as its name implies, it is a displacement transducer. So this transducer will be attached with the mass, and with reference, if any change in due to the earthquake, if any change in position takes place, and it will be measured by the LVDT sensor, and this sensors will be calibrated, that is changing distance will be calibrated into electrical voltage. Changing distance due to the earthquake's sake, distance will change between the mass and the frame, and it is recorded by means of LVDT's transducer, and it is calibrated. It is previously calibrated in such a way that every change in distance will be converted into its equivalent voltage, that is electrical signal, and then it will be amplified and used for recording. Okay. So modern devices use electronic sensors and amplifiers in order to get more accurate data. So the next one is Richter scales. Richter scale gives information about magnitude of earthquake. Suppose if you want to compare earthquake magnitudes at different places, location A. The location A magnitude is, imagine magnitude is 5, and in the location B, magnitude is 1. If earthquake 1 Richter scale and 5. Now let us compare how these numbers going to represent the power or intensity of earthquake. So magnitude equal to log at location, intensity at location A divided by minimum intensity, and in this case magnitude at B equal to log of intensity at B divided by minimum intensity. So here magnitude is 5, IA by I0. Here magnitude is 1, so 10 power 5 IA by I0, 10 power 1 we just divide these equations, 1 and 1 divided by 2, you will get 10 power 5 by 10 power 1 equal to IA by I0 into I0 by IP. I0 will cancel out. So finally you will get 10 power 4 equal to IA by IP. IP into 10 power 4 equal to IA. So at location B, magnitude is, that is a Richter scale magnitude is 1, and it's at location A it is 5. So if you compare these locations, magnitudes, at location A, intensity or power of magnitude is location A is 10 power 4 times larger than at location B, which is having Richter value of 1. So 10 power for such a small difference, 5 and 1 Richter scale, in Richter scale, you will, the actual difference or earthquake's impact or power of earthquake or intensity of earthquake difference will be 10 power 4 times, 10,000 times of difference you will get. So that is how even a 0.1 value of difference in 0.1 value of Richter scale, it gives a lot of impact on earthquake's magnitude or intensity. So any small change is a very important matter here. Okay. And next one is, we will see some of the applications of seismology. That is how to use seismograms. Applications. Suppose if you have recorded seismograms at different locations, location A, or at different stations, station A, you use a seismometer and you get data like this. Something like that. So this one, P wave, S wave, and low wave, Raleigh waves. Love wave, Raleigh wave. At station B, keep in mind here x-axis is time. So time taken for the P waves, the time difference between P and S waves is 1 minute. And here roughly it is about 2 minutes. And station B, station C, P wave, shear waves, love waves, Raleigh waves. P waves, shear waves, love waves, Raleigh waves. And here the time difference is around 3 minutes. So 3 minutes is the time difference. So using 3 different seismometers, you are going to record earthquake or seismic waves at 3 different stations, and your data like you get different data like this means. Now we will see how to interpret these data and how to identify the location of epicenter from where surface waves are emerging. And there is a graph between distance in kilometers and time taken. Here time taken for the waves is 36 minutes from 0 to 1, 2, 3, 4, 5, 30 minutes, and distance from the epicenter is 0, 1000, 2000, 3000, 4000, 5000, 6000, 7000 kilometers. So now you are going to fit the data of 3 different stations, and 3 different stations. Just imagine station A. P wave starts at here, and then S wave starts. I'm going to skip low waves and Raleigh waves. Okay. Now P wave started, and then S waves going to start. Another station, different stations, and shear wave 1 at here, shear wave 2, shear wave 3. Keep in mind, I have skipped test of low and rolling waves. Now I am going to make a line. It starts from the origin, P wave 1, you will get a parabolic or a non-linear curve. It's a non-linear curve you will get. And in the case of S wave starts from here. So it takes 1 minute for the station. The time taken from for the S waves to start is about 1 minute. And here 2 minutes it will take. After 3 minutes only, S waves will be realized in the station B. Now, so you will get a non-linear curves like this if you bring all the data in a single graph. Keep in mind y-axis gives information about time. So when the time difference is 1 minute, the distance, corresponding distance will be about 2000 kilometers. It means this station A, station A, station B, station B. Station A is located 2000 kilometers far away from the epicenter, and station B is located 3500 kilometers far away from the epicenter. Similarly, station C located 6000 kilometers far away from the. So that the time difference between P and S waves is very significant. Based on the time difference, you will come to know how far it is or how close it is with the epicenter. So if the time difference increases, means these stations, that is seismometers, are located far away from the epicenter. And if the time difference is very short, means these stations, particular station is located very near to the epicenter. Okay. So this is the one application of seismology. So by using seismology and its data, you can interpret to get information about where earthquake is started, from where earthquake is originated. Okay. And next one is, it is also based on the change in time and the change in time between P and S waves, of course low waves and rolling waves. One can interpret nature of the earth and also nature of any planetary system. Suppose if you mount some different seismometers in Mars and any moon, any other planet, any other celestial object at different locations. In a similar pattern, if you record seismometers and interpret like this, you will come to know different layers of any celestial objects. Okay, any layers of celestial, and you can interpret their properties, their what type of composition, all those things. You can speculate all those things. Okay, that is the application of speculate the composition and nature of the celestial objects or earth. And also you can exactly locate from where earthquakes started. Okay. So these are some of the applications. If you have any doubt, feel free to ask any kind of questions.